Oh, hey, hi, hello. This is 2582. Please pass the pillow. Okay. So there are n people standing in a line labeled from 1 to n. That's a familiar problem statement that we've probably encountered several times previously. 1 to n. Usually that indicates we're going to be creating an array. We're going to do some sort of iteration through this array relating to the objects within the array. Something like that. 1 to n. Typically, that's the kind of problem that you're dealing with. The first person in the line is holding a pillow initially. Okay. Every second, the person holding the pillow passes it to the next person standing in the line. Okay, so this is very easy to imagine, right? You have these group of people, there's n people, they're standing in a straight line together. One of them has the pillow at time t. At time t plus 1, they give it to the person that's next to them. Once the pillow reaches the end of the line, the direction changes and people continue passing the pillow in the opposite direction. Okay, so you can kind of imagine, person's holding the pillow, they pass it to their right, they keep passing it to their right until they get to the end, until the pillow gets to the end of the line, because the person at the end of the line is going to be holding the pillow and be like, well, I got no one to my right to pass it to, so they're going to pass it left. And now people are going to pass it left until it gets to the beginning of the line. And then when it gets there, if there's still time remaining, that person's going to have no one to pass it to their left, and they're going to have to pass it right. So you can kind of just see how it alternates, right? The pillow starts in one position, it moves all the way over until it reaches the end, and then it moves all the way back, and it keeps doing that until you run out of time and you determine what position you're going to be in. Okay, so for example, once the pillow reaches the nth person, so that's the final person, they have no one to their right to give it to, like I said, so they're going to pass it to the nth minus 1 person, so they're going to pass it to the left. And so then the nth minus 1 person is now going to respect that direction, and they're going to give it to the nth minus 2th person, and so on. Right, so this problem has a system where you need to think about direction, right? Because, when you have the pillow, you might pass it left or right depending on what direction it was given to you, right? If everyone's passing it left, then you pass it left. Everyone's passing it right, you pass it right, if that makes sense. And so on, right? If you got it from your left, you're going to keep passing it right. If you got it from your right, you're going to keep passing it left. If you're the 0th person, you're always going to pass it right because you have no one to your left to give it to. If you're the last person, you're always going to pass it left because you have no one to give it to on your right. Okay. So given the two positive integers n in time, return the index of the person holding the pillow after time seconds, right? So you're just trying to keep going through this whole system until you find when time equals 0, right? When you go through all time seconds, who's holding the pillow? All right. Now, the easiest way to solve this would be just the assimilation. So let's just go ahead and look at that quickly, right? So if we had, in this example, n equals 4 people, right? So we have these 4 fellows standing in line, right? Sorry, I'm going to make their heads a little bigger so I can specify. We got big heads because they do a lot of Leetcode, so their brains are massive. Okay, so this is person 1, this is person 2, this is person 3, and this is person 4. And then these people, they have this little green pillow, don't ask me why it's green, that they're going to pass around for 5 seconds, right? So the way that this works is person 1 initially has the pillow. After 1 second, person 2 has it. After 2 seconds, person 3 has it. After 3 seconds, person 4 has it. Person 4 has no one else to give it to on its right. So after 4 seconds, 4 is going to pass it back to 3. Now the direction changes. And then after 5 seconds, person 2 is going to have this pillow, right? And that's why the output is 2. So if you want to do it again, 1, 2, 3, 4, 5. Sorry, there's a little bit of a delay, but you see what I mean. 1, 2, 3, 4, 5, right? So it passes and then back. If it was 10, right, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would end with person 3. So there's this alternating idea. So technically, given the constraints, right, with n less than or equal to 1,000, time less than or equal to 1,000, you could solve this via assimilation, right? You could have a starting value and a direction, or starting index is 1 in a direction, and go all the way to the right until you reach n, and then change directions, and then just loop through all time seconds and figure out where this object is at the end. But something kind of intuitively implies to me, right, in my soul, that there's some closed form solution to this, right? Because it's like, there's a closed system, there's n nodes, there's time seconds, there's got to be some sort of divisibility way, there's got to be some sort of way to determine where this is going to be at the end just by looking at those two numbers individually and doing some sort of operation, right? And I guess what will lead you to that answer is to think about, if this problem was slightly different, how would you solve it easily using math? Okay, so let's adjust this problem. So we're going to make a modification quickly, a small modification to allow us to solve this, to give us some intuition about how this problem is going to be solved. Okay, so the modification I'm going to be making is nth person passes back to first person. So what I mean by that is the nth person passing it back to the first person is, instead of the direction changing, how would this problem be solved if 1 passed to 2, then to 3, and then to 4, and then instead of going back to 3, 4 lobbied it, like, woo, threw it, Tom Brady style, back to 1, right? And then 1 to 2, and 2 to 3, and 3 to 4, and then lobbied it back to 1, right? So what would the problem look like then? How could you easily solve it then if it wasn't the case that, we go all the way to the right, then back left, then back right? Instead, we go all the way to the right, then we restart, and we go all the way to the right, and we restart every single throw, every single pass at every second, right? So, for example, in this new problem, if we had time equals 7 and n equals 4, how would this work? Well, we could do the simulation again, right, where 1, 2, 3, but after 4 seconds, we're back. 4, 5, 6, 7, right? So in this system, if we lobbied it back all the way to the front, it would end with person 4, right? Now, why is this new system easier to solve? Well, the thing is there's a cycle in the system, right? There's a cycle in the system where, like, if you go more than 4 seconds, you're going to end up right where you started, right? Because it starts with 1, right? But then after 4 seconds, 1, 2, 3, 4, right? 1, 2, 3, 4, it ends up right back to where it started, right? So you start in position 1, right? Equals 1. And then you're going to go 7 steps forward, right? You're going to move 7 times, right? But really, after you move 4 times, you move 4 plus 3 times, right? But when you move 4 times, you end up back where you started, right? What I'm basically saying is, when I move 4 times, if there's only 4 people, I end up right back in the beginning in this problem, right? When I start at person 1 and I move 4 times, 1 time, 2 times, 3 times, 4 times, right? I end up right back to where I started. Okay, so when I move 4 times, I don't need to think about that in my final equation, right? This gets x'd out, right? This gets x'd out. What really matters is the difference here, 3, right? Because after I move 4 times, there's only 3 remaining. So 1, 2, 3. So whatever the ending position is with respect to where I started is what I care about. But the fact that I moved 4 times back is uneventful, because I kind of just absorb those 4 moves, because it comes right back to where it started, right? So again, I guess a different example to think about, yet again, is, you always start at position 1. What if we were going for instead 13 seconds, right? What if time was 13 seconds? Well, we're going to move 13 times, right? But again, there's going to be this issue where, I move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's the same thing as only moving 1 position from the beginning, right? And why is that? Well, because 13 is really 4 plus 4 plus 4 plus 1, right? So this 4 becomes a 0 and 0 and 0. And what I mean by 0 is, like, why is it 0? Is because it's uneventful, right? If I go 4 positions over, well, that's just n. So if I move 4 over, I just end up right in the same spot, right? So really what we're looking at is, well, this equation here, right? What I'm doing here is effectively what? I'm effectively doing modular arithmetic. What I'm saying is, I don't care the amount that I go. I just care about the offset from where I started and where I'll end up. So every time I go 4, I'm going to remove that from the system. So really, it's just taking the modulo of this thing by 4, right? Because the modulo of 4 is basically saying what remains when I keep dividing out 4, because I'm going to keep going 4. But every time I go 4, I don't care, right? Because the amount that I go 4 is just going to lead me back to the same spot. The amount that I go n will just lead me back to the same spot. If I go 4 starting from 1, I'll end up right back at 1, right? If I go 4, 1, 2, 3, 4, I end up right back at 1. So I want to just get the offset from me that I'll end up being. And that's what 13 mod 4 will give you, right? Because 13 mod 4 will say, well, what's the remainder when I remove factors of 4, right? So what's the remainder when I pull out all the 4s that get me nowhere, right? That's what 13 mod 4 is essentially going to give me. And that will give you 1. So then my final position is 2 using this logic, right? So this here is my offset from starting position. Right, so my starting position plus my offset from starting position is my ending position, right? And the reason why this works is because when I use a modular equation, what I'm essentially doing is I'm just caring about the offset because I'm going to divide out the whole like cycles that I'm going to commit to, right? When I do 13, I'm going to end up doing 3 cycles of 4. So when I do modular, I'm just taking out the remainder. What remains when I do these cycles, okay? So that means that the general equation then, right, what was 13 and what was 4 in this equation would be the starting position 1 plus the amount of time that I'm going modular n, right, the size of my system to determine the number of cycles within my system, okay? So this would be the generic equation for this problem here. But the issue is, right, that this is a, this is a modified version of the problem. So how do we deal with the fact that we're going forward and then we're going backwards and going forward and going backwards instead of thinking about the fact that we just go forward and we start back at the beginning, right? Because we want to use this idea because we have this closed form solution, but it's not the same because we're dealing with the scenario where, you're just passing, in one direction and then back in the other direction, then in one direction and back in the other direction. So the way that we can do that is by taking this problem here and modifying it the way that we think about the people slightly so that we can model it as the problem up here, right? Because the problem up here, essentially what we did was 1 passes it to 2, to 3, to 4, and then back to 1, right? There's this cycle system, so then we can figure out what the length of the cycle is so we can determine, what we can pull out to just find that offset from the starting position. So here, when it gets to 1, to 2, to 3, to 4, who's 4 going to pass it to? Well, 4 is going to pass it to 3, right? And who's 3 going to pass it to? 3 is going to pass it to 2, right? If 4 gets the item, he's going to pass it back to 3. But okay, we'll just say then pass it to 3 here. If 3 gets the item from 4, he's going to pass it to 2. And if 2 gets the item from 3, he's going to pass it back to 1. So now we can look at this system in a slightly different way so that we can use this equation above, right? Because we wanted it to look like this so then we could use this closed form solution to solve it, right? Because we want to think about the nth person passing it back to the first person so we can think about it in terms of offsets. So what if we just model the system in the same manner so then we can also think about it in terms of offsets, right? So when 1 gets it, they pass it to 2. When 2 gets it, they pass it to 3. When 3 gets it, they pass it to 4. When 4 gets it, they pass it back to 3. When 3 gets it, they pass it back to 2. When 2 gets it, they pass it back to 1. When 1 gets it, he passes it back to 2. When 2 gets it, he passes it back to 3. See, so this system still, if you think about it in terms of the initial problem, right? In the initial problem, it went from 1 to 2 to 3 to 4, back to 3, back to 2, back to 1, to 2 to 3 to 4 and so on and so forth. And that's the same thing here, right? We go from 1 to 2 to 3 to 4 to 3, back to 3, back to 2, back to 1 to 2 to 3 to 4. So you'll notice that just by tweaking the way that we model this problem, we can describe it using this equation. But the difference is well, we're no longer dealing with n, right? We're no longer dealing with n because n was the number of people in our system, right? But now we've added additional people. So how many people have we added? Well, we have n people here. And then we add these additional dummy variables, n minus 2. So if we add these together, our new equation, we have n people plus n minus 2 people. So that's, let's do some algebra here. So that's 2n minus 2, or 2 times n minus 1 people. So then our...
Minus 2 times 2. Minus 1 is minus 5.
Alexa just went off. Okay. So that means that we have a starting position of 1, and our ending position is time mod n. So time is the same. And then we're going to mod it by 2 times n minus 1, like so. So this would be our final equation, sort of. But the only issue is right, this is going to indicate that, you know, this is person 1, this is person 2, 3, 4, 5, and 6, right? So, right, if we run this, the problem is like this equation works because it'll tell you the offset, but we still have the case where, you know, when you're at person 4, you're at person 5, you're not really at person 5, right? Because we remodeled the system. So you're not, even though you're 5 away from the initial 1, you're actually at person 3, right? And when you're at person 2, you're at 5 away from person 1, right, in this system, but this equation will tell you that you're at person 6. So to combat that, we'll say, well, you know, what's this 5? Okay, so then we need to think about what this 5 is with respect to this 3. What's this 6 with respect to 2? So this is 4 minus the distance to the next thing, right? So this is... So this equals 3 because it's 1 away from 4 minus 1. And this is 5 and it's 1 away. So this is... I'm trying to think of this in terms of an equation. So this right here is going to get a little confusing here. This is our answer x. So it's 4 minus the answer x. Or no, shoot, the other way around. X minus 4. Right? Because we're trying to get the distance from 5 to 4 to get our offset correct. Right? So if x is 5, that's 4 minus 1. If x is 6, 6 minus 4 is 2. 4 minus 2 is, so let's, so this is 2 times n minus x. So that's the generic equation for this here, right? But does that work for these ones? Because 2 times 4 is 8, minus 3 is 5. No, so it's on the wrong. So only if it's greater than 4, then you have to make this offset, right? Because over here, the numbers match 1 to 1, right? 1 is 1, 2 is 2, 3 is 3, 4 is 4. But then after you go over n, since we added these dummy variables that aren't actually represented by their distance from our initial value 1, we need to use this equation. So I think we can do that by just saying, we'll use this if we're less than or equal to n, and then we'll use 2 times n minus this if we're greater than or equal to n, right? If our value is greater than or equal to n. Huh. So I think you could just do the min. So you could just say, well, we're going to return the... So we know that... Let's just do the equation first, right? So our equation is 1 plus time mod 2 times n minus 1, right? So we'll return the min of that and 2 times n minus all of that. And whichever one is smaller should be the appropriate one. All right. So maybe it would be easier just to do the simulation so you don't have this answer that's like, what? But this is technically the optimal approach, right? The only issue is, like, since we created these dummy variables, this isn't actually person 5, right? This is person 3. So you just do the min, because the min will either be, if it's smaller on this side, then we'll pick this. But when you get past 4, it'll actually be smaller on this side. So, right, because on the other side, these values would be 5, 6, 7, or whatever. Okay. All right, so what is the space and time? So the brute force kind of just simulation approach, that would be O of time, right? Because you have to do O time iterations. But this one would be time and space. For time, well, we just do a constant operation, right? This is a constant operation. It's a little tricky looking, but this is a constant operation. These are constant operations. So that's O of 1. And then for space, we're not creating anything additional. We're just calculating the min of 2 things. O of 1, O of 1. All right, guys, peace out.